Okay, ladies and gentlemen, so we are on 3.4, which is velocity and other rates of change. So this whole first page is all notation and the breakdown of how to find these various vocabulary words. So an object is moving along a coordinate plane so that its position s of t. The object's change in position, change in s, is its displacement over a time interval. So displacement is equal to the change in the position. So displacement will have a direction. It'll either be positive or negative. So if we look at this graph, if I were to pick 2 points on this graph, let's say I pick this point here and this point here. The displacement would be from 700 to 500. So the displacement would be a positive 200. Alright, so the average velocity is the displacement over the travel time. So if we look at our same points, we said that our displacement is a positive 200 and our change in time is 1 second. So our average velocity, change in s over change in t, is equal to 200. In this case, feet per second. Our instantaneous velocity, that's when we get into the derivative. So our instantaneous velocity would be the derivative of our position function, so our derivative of s of t. So instantaneous velocity is the same thing as s prime of t, which is ds dt. So all of that is the same. And then our speed is the absolute value of the instantaneous velocity. And our acceleration is the second derivative of our initial position function. So a of t is equal to the derivative of v of t, which is the second derivative of t, which we can rewrite as d squared s over dt squared. Okay, let's move on to page 2, where we get into some examples. So a student walks around in front of a motion detector that records her velocity at 1 second intervals for 36 seconds. The data generated the following velocity graph. So this is a velocity graph. So let's remind ourselves that s prime of t is equal to our velocity. So we're looking at the derivative of our position function. And we are on 1 second intervals from 0 to 36. So if we were to count up our tick marks or notate our tick marks, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 tick marks. So we're going by 4s. 8, 12, 16, 20. Just to make sure that we're going at the proper pace when we write down our notation. So our first question says, when will the student be standing still? So we know that if somebody is standing still, that means that they are not moving. They have no velocity. Their velocity should be 0. So what we're looking for is she is standing still when v of t is equal to 0. So if we look at our graph, we know that v of t equals 0 various parts. So we know it equals 0 here, 0 here, and 0 from about here to here. So this whole section here. So since those are when v of t is equal to 0, we know she's standing still at time 0. That's about 14. And these are seconds. And from about 26 to 32. Oops. 26 to 32. Wow. Notation, notation, notation. Okay. So next thing we want to know is when does she begin moving forward? So since we're looking at a velocity graph, we know that velocity is the derivative of the position. So when she's moving forward, that means she's moving in a positive direction. And so our velocity should be positive when she's moving forward. When she was moving backwards, our velocity was negative. So in this case, she moves forward when v of t is greater than 0. And those moments are from 0 to 14. To 14, and from 32 to 36. Now we know when she's moving backwards, that's when our velocity is negative. So she moves backwards when v of t is less than 0. And from our graph, we know that happens from 14 till about 26. Next thing we want to know is when will the student reach her maximum speed? So we know that speed is equal to the absolute value of v of t. So we want to know when is v of t, the absolute value of v of t, the greatest. So when we look at our graph, up here, v of t is 4 or so. Down here, v of t is -7. So we have 4 and we have -7. However, we want to know, if we take the absolute value of 4 and -7, which number is greatest? And that value is -7. So at about t equals 20, we have this point, although it is a minimum, remember we're taking the absolute value of that, -7, the absolute value of -7 is greater than the absolute value of 4. Therefore, at t equals 20, v of t equals -7. absolute value of v of t equals 7. So she reaches her max speed of 7 at time t equals 20 seconds. Okay. This last piece is when is the student's acceleration 0? So let's remind ourselves that acceleration is equal to the derivative of t. So if we want acceleration to be 0, then we're looking for when is the derivative of t equal to 0. Okay, so we're looking for when is the slope of our graph equal to 0? So if we go back up to the top, our slope is 0 when we have a horizontal line. So we have a horizontal line going on up here from about 4 to 8. We have another horizontal line, a small one, happening down here at t equals 20. We have another one happening here from 26 to 32. So we have 3 moments when our graph is going to have an acceleration of 0. So from 4 to 8 at t equals 20, and from 26 to 32. Okay, let's move on to the next page. So now we have a particle that moves along a horizontal line y equals 2, so that this position at any time from 0 to 7 is given by the function s of t equals 2t cubed minus 18t squared plus 48t minus 40. So our first question is to find the displacement of the particle during the first second. So let's remind ourselves, displacement is the change in speed. And if we're looking for the displacement within the first second, then we're going to be looking for s of 1 minus s of 0. So we know that s of 1, if we plug in 1 into our equation, we get negative 8, and we're going to subtract s of 0. When we plug in 0, get negative 40. Positive and positive make negative, and a negative make a positive, so we have negative 8 plus 40, which is a positive 32 meters. And that is our displacement. Second question asks us to find the times when the particle is stopped. So if we remember from our first example, the particle is stopped when v of t is equal to 0. Okay, and we can rewrite v of t as the derivative of s of t. So we're looking for the derivative of the position at 0, when it equals 0. So to find the derivative, we'll just use power rule. So we have 6t squared minus 36t plus 48, and we want that to equal 0. So we can factor out a 6 from all of these terms. We have t squared minus 6. Oops, not t squared, just t. No, right. T squared, sorry, minus 6t plus 8. And we can factor t squared minus 6t plus 8. So we get 0 is equal to 6, t minus 4, t minus 2. So from here, we know that the particle is stopped when t equals 4 seconds and when t equals 2 seconds. Next, we want to find out when the particle is moving to the left. So to do this, I'm just going to create a little number line, and I'm going to start it at 0 because that's the interval that it gives us from 0 to 7. So I'm going to start it at 0, end it at 7. And we know that the particle stops, so v of t is stopped at 4 and 2. So I'm going to put 2 and 4. Okay, so these numbers up top are my time, and down at the bottom, these are all my velocities. So we know at 2, the velocity is 0. At 4, the velocity is 0. So in order for there to be a velocity of 0 here, that means that we had to have changed signs. Okay, this is called a sign table. Okay, we're going to show what's the sign between 0 and 2, between 2 and 4, between 4 and 7. And to do that, we really just need to know what's the sign for one of them, because we know that once we change signs, we're just going to write the opposite sign. So between 0 and 2, if we plug in 1, for example, we find out that our sign is positive. So when we change signs, we go negative, and then when we change signs again, we go positive. So we want to know when is the particle moving to the left. So we want to know when is v of t less than 0. So when is the sign going to be negative? And that happens between 2 and 4. So the particle moves left between 2 and 4 seconds. All right. For D, we want the speed of the particle when t is 3. So again, speed is equal to the absolute value of velocity. So we want the absolute value of the velocity when t equals 3. So to do that, we want the velocity of 3. And when you plug that in, you get negative 6. And then we're going to take the absolute value of that, which is positive 6 meters per second. E wants us to find the acceleration of the particle when t is equal to 4. So, reminder, acceleration is equal to the derivative of velocity. And if we look at our velocity equation, this was our velocity equation. we're going to take that and take the derivative. So we'll have 12t minus 36. And we want the acceleration at t equals 4. So we'll have 12 times 4 minus 36, which is equal to 12 meters per second squared. Acceleration is squared for seconds. Okay. Now, we want the average velocity during the first 2 seconds. So average velocity is equal to change in position over change in time. So if we want it in the first 2 seconds, then we're looking for s of 2 minus s of 0 over 2 minus 0. So this brings us all the way back to our original function up top. Okay, this is the position function. So we're going to plug in 2 and plug in 0. And when we do that, we get, when we plug in 0, we get negative 40. When we plug in 2, we get 0. So 0 minus negative 40 over 2. Negative and negative is a positive. So 40 over 2, which is equal to 20 meters per second. Those are the notes for today. You will be working on various worksheets throughout the week to help you practice before Friday's quiz.